communication between NameNode and data nodes, where data nodes will be sending signals for every 3 seconds, and the 10th heartbeat will be the block information. And we even discussed that if the heartbeat was recognized to be failed, so NameNode will make another replication always to have 3 healthy replications across the cluster. This is what we discussed yesterday. Now, let me talk about one of the most important and the quite common occurring issue in the environment, which is because of the network. So let me address about it. So if you observe here, let's say all the data nodes, whatever they represent in the cluster environment, they are sending the signals to the name node. All the data nodes are sending the signals to the name node. That's what we know. All of them are sending signals to the name node. Let's say only this specific data node, except this specific data node. Let's say name node could able to receive all the signals from all the data nodes except this specific data node. And since it cannot receive or it cannot identify any heartbeat from this specific data node, NameNode will consider this specific data node was dead, and so it will go on with making another replication. And so it has, if you observe here, it has 2 replications currently for this specific data node. For this specific block, it has identified that it was under replicated, and it will make another replication. So this is what we discussed yesterday. So let's say block 2 was replicated again here. So as per name node, there were 3 healthy replications across the cluster. Now coming to the point why this data node was failed, as I specified yesterday, it can be a disk failure, a power failure, or a data node service failure, or a network failure. Let's say the node is absolutely fine. Node 2 of rack 3 is absolutely fine. It doesn't have any physical problems. Node 2 of rack 3 is absolutely fine, but the problem is between the network. Because there can be some situations which quite frequently occur in the environment because of these network issues, network transmissions. So let's say the problem is between the network, between this node and this node. And since there was a problem, absolutely NameNode cannot identify any heartbeat from this specific data node. It will not identify that. And so it made the other replication. Now after a few minutes, after making this replication, let's say the network issue between these two got resolved, and NameNode can find the heartbeat even from this data node. So at that situation, if you observe, NameNode can clearly identify 4 replications of block 2. 1 replication, second, third, and 4th replication. So NameNode can identify simply 4 replications of block 2. 4 replications of block 2. And this is the case called as over replication. If it is below the 3 replication factor, we'll address that as under replication, and if it is above, it is what we call as over replication. And the case of over replication, NameNode does not have any right to delete the over replicated blocks. It will be popping up with a message to the administrator, where administrator then types a command called as file system check, FSCK. No sooner than when the administrator type the command, it will give what are called the over replicated blocks on which node. So administrator need to connect to that specific node manually, and then he need to delete the over replicated blocks, and that too he need to perform the action as per the rack awareness only. So it's a manual approach. It's not the automized approach that happens usually on top of the environment. All right. So this is one of the important case study. And so far, even till now, we've been talking about the communication between NameNode and data nodes. Let's see the NameNode's anatomy, how the NameNode has all the things going by. As I shared yesterday, you'll have file name, file size, block size, replication factor, timestamp, permissions, user group. You'll have block IDs. So this is what you'll have all in the NameNode's metadata. And the block information will be constructed to the heartbeats. This is what we discussed, right? And we even came to know that the same file system, the same details except the block information will even be stored on top of file system image in a hard disk, right? File name, file size, block size, replication factor, user group, permissions, timestamp, and you'll have block IDs. Now, we know that when a file was uploaded to the cluster environment, the entry will be made in the NameNode's metadata. That is what we discussed. For each and every file upload, an entry will be created in the NameNode's metadata, not in the NameNode's hard disk, not in the FS image, simply. For each and every file that you upload, an entry will be created in the NameNode's metadata. Now let's say, now the time is something like 7 o'clock. Now it is 7 o'clock. So let's say at 7 o'clock, you have totally 100 files in metadata. And since the NameNode was just started, so obviously you'll have the same 100 files here also. Totally had 100 files. Now my question is, let's say at 7:05 a file was uploaded. A file was uploaded at 7:05, so you'll have 101. 7:30 a file was deleted, so again you'll have 100. 7:40, let's say one more file was uploaded. 7:55 one more file was uploaded. 7:58 one more file was uploaded, and 7:59 one file was deleted. And at 8 o'clock. So if you observe the snapshot between 7 o'clock and 8 o'clock, there were almost 1, 2, 3, 4, 5, 6. 6 modifications made in the metadata. There were several modifications being made in the metadata, and let's say 8 o'clock, NameNode got a partial failure, or let's say RAM was failed. So when the team restarted the NameNode, again this FS image will be loaded into the RAM, but this FS image do not have those modifications. All the 6 modifications, whatever made, are not present in the FS image. They were modified only in the metadata, which is in the RAM. So there should be a particular mechanism which will always keep the FS image in it, which is present in the hard disk, and the metadata, they should be always kept in sync. And that job of keeping metadata and FS image in sync will be taken care by secondary NameNode. most important. Secondary name node will take that privilege. How? Let's see at a high level, and of course within few minutes we are going to delve much more deeper into the discussion. So let's say there was an entry created in the metadata at 7.5. The same will be reflected in the edit log. At 7.20, one more modification was reflected. Again, that will be reflected here. Edit log is part of RAM present in the name node itself. At 7:40, one more file was added. The same will be reflected. And at 7:45, a file was deleted. The same will be reflected. And at 7:55, a file was uploaded. 7:57, one file was deleted. So all these modifications, whatever the modification that will be made in metadata will be immediately reflected in the edit log. And exactly at 8 o'clock, that means for 1 hour, secondary name node will fetch the edit log and it will fetch the FS image, where it will merge them together. And this is what we call as snapshot. This is what we call a snapshot. So for every 1 hour, there will be a snapshot made by default. For every 1 hour, a snapshot will be made. This is what we call as a snapshot. Once after the snapshot was made, the latest FS image, indeed, snapshot gives you the new FS image, which had all these modifications kept in sync. So that new FS image will be sent back to the name node, overriding the old FS image. Because this new FS image is required for 9 o'clock snapshot. So that's how it will keep on sync. Let's delve deeper. So here you can see modifications made in the metadata will be reflected in the edit log. Metadata will have the block information, but FS image will not. I think we already discussed about that. FS image will not have the block informations, but FS image is snapshots. FS image is required for the snapshots, where snapshots will be preserved with the second name node. Let's delve deeper how the snapshots will be made. So here, as discussed, for every 1 hour, I repeat, for every 1 hour, by default, the configuration will be made for every 1 hour. We'll address that as a periodic snapshot. A snapshot will be made from the name node by the secondary name node. So let's say now the time is 7 o'clock. So as per 1 hour snapshot, we have the next schedule at 8 o'clock, right? So 7:05, a file was uploaded. Obviously, when a file was uploaded, the same will be reflected in the edit log. You can even physically see these edit logs on, most probably, as I specified, upcoming Tuesday, we're going to build the cluster. So once the cluster was built, we can see all these things physically. FS image and edit log, you can see that physically. So 7:05, an entry was made in the edit log. 7:15, one more entry was made. 7:20, file was deleted. 7:35, a file was uploaded. 7:50, file was deleted. 7:50, file was deleted. The same will be reflected here. And 7:58, a file was uploaded. So exactly at 8 o'clock, you'll have a snapshot. Now, let us delve deeper much into this. So 7:58, once after the last update was made, 7:59, that means exactly just 1 minute before the snapshot snapshot, NameNode got failed. Just 1 minute before the snapshot, let's say NameNode got failed. Obviously, at that time, whatever the modifications made in the edit log will be lost. You will not have those modifications reflected in the FS image. That will be a hazardous situation because you are going to lose your information. And so, again, at that situation, let's see how the NameNode was configured. So, NameNode perspective, at the edit log level, a threshold limit will be defined. It usually will be defined for every 5 records. So, let's say the threshold will be defined for 5 records, or let's say only 3 records. So, as I specified again, 7 o'clock and 8 o'clock. 7:05 a file was uploaded. Same will be reflected. 7:15 one more file was uploaded. Same will be reflected. 7:35 a file was deleted. Same will be reflected. That means at 7:35 the threshold limit was reached, and so at 7:35 it's going to create a new FS image. We'll address this as snapshot. So a snapshot will be made at 7:35 because the threshold limit was reached. So at 7:40 one more file was uploaded. The same will be reflected. 7:45 let's say deleted, and 7:50 one more file was uploaded. So exactly again at 7:50, 7:35 you have a snapshot, 7:50 you have a snapshot. These are all the threshold limit snapshots. And at 7:56 a file was uploaded again, and 7:58 a file was deleted. 8 o'clock the threshold limit was not reached, but since it was a periodic snapshot, again the periodic snapshot will be made at 8 o'clock. So the snapshots will be made not only confined to the periodic limit, but also confined to the threshold limit. That's how the snapshots will be configured. Now let's even delve deeper much more. So we know that 7:35 there was a snapshot made, and 7:50 there was a snapshot made. So as per our requirement, I mean the periodic snapshot, we have 8 o'clock snapshot already scheduled because that's the hourly snapshot. So 7:50 there was a snapshot. 7:54 a file was uploaded. 7:58 one more file was uploaded. And at 7:59, that means just 1 minute again before snapshot, NameNode got failed. And observe these two records, they even did not reach a threshold limit. They even did not reach the periodic time. So definitely again, there might be a hazardous situation of losing these two records. In order to eradicate that, there was a temporary solution where usage of NVRAMs, non-volatile RAMs, which will not give you the privilege of losing the data, can save you up to some extent. Up to some extent, it can be saved on. But when the data rush is huge, even they'll not work out. So owing to that, in Hadoop 2, in the latest version of Hadoop, they came up with a solution of maintaining n number of name nodes across the cluster. So you'll have 3 to 4 name nodes, where all these name nodes will have a common shared edit log. They'll have a common shared edit log. So whatever the modification made will be reflected to all, and so if any one was failed, no problem, other will always be in sync. So we'll talk about that, the NameNode high availability concepts, in the upcoming discussion. But actually this is how the snapshots will be made. how the name node and secondary name node will be communicating. And even in this case also you'll have the secondary name node required, because to empty this edit log definitely require the secondary name node. Secondary name node job will release that edit log because it will flush the edit log into the FS image, right? And here you can see always the latest snapshot will be sent back to the name node because that is required for the next hour's snapshot. And here we have the snapshots or periodic snapshots where for every 1 hour, and the snapshots when reach a threshold limit. Well, the threshold limit can be defined, it can be customized, and the latest snapshot will always be sent back to the name node, keeping a copy in the second name node. So this is how you have name node and secondary name node always kept in sync, right? So far we discussed how the name node communicates with data nodes, and just now we discussed how the communication happens between name node and secondary name node. And as I specified, there will not be any communication between secondary name node and data nodes. So this is the discussion. Now, let me talk about the MapReduce. So far, whatever we discussed is only at the range of HDFS. We have been talking about how the data was getting stored, how the data will be maintained high available, how the metadata will be maintained, and how NameNode will be looking after an entire cluster, how a file will be uploaded, how it will be retrieved. So we have been talking about only the HDFS operations. But indeed, since with the developers need to focus much on the MapReduce perspective, processing the data sets, not on top of storing the data sets. Now let's switch on to the MapReduce environment. But before switching on to that, if anything unclear till this moment, the entire HDFS discussion, just kindly shoot me. If not, let me continue.
Vignesh, I have a few questions here. We talked about communication between name node and secondary name node. Is there any periodical scheduling is a 1 hour? You said 1 hour, right? So the 1 hour is a constant time period, or can we make?
You can change it. You can change it. By default, it comes with 1 hour.
Okay. Even the threshold is also somewhere like 30 minutes. So 30 minutes.
No, threshold limit will not be confined to time. It will be confined to the heap memory, whatever the entries that were made. So let's say at the range of RAM level, there were 5 entries made. So at 5 entries made, there will be a snapshot created. It will be confined to the number of entries made, not confined to the timestamp.
Okay.
Right?
Okay. And also for this, do you have any?
Please tell me.
This? For this periodical schedule, do you have any background process for this, like to schedule jobs for this? To make a sync with
periodic snapshots.
Yeah, for your periodic snapshots.
No, we'll not be having any other daemon running on actually. It's the default made by, because NameNode and secondary NameNode itself are the daemons which will be running background by default. So by default, when it reaches the threshold limit, you'll get the things done.
Okay. Okay.
Yeah.
Vignesh, one question.
Please.
You said like a over replication is going to identify by admin by executing some commands, unique commands.
FS6, yes.
Yeah. And is there any way like under replications going to identify?
No, because if there was any under replication, by default NameNode will make it replicated, right?
Okay.
No sooner when it found any under replication, by default it will going to make 3 replications.
Okay. Okay. This is going to like just constantly. Yeah.
Yes, he need not worry regarding that. Provided your question will be valid, let's say the cluster size was full, a NameNode cannot replicate the third replication to any one of the data node. Then it will pop up even with the same FSCK command. It will just pop up with the under replication blocks. These are all the under replication blocks. It will pop up, but it will not happen usually because if there is availability, definitely it will go for the third replication.
Okay.
Right. So now let me talk about MapReduce. Indeed, I can say a massive parallel approach of handling the data assets. MapReduce. The name itself conveys us. It has two phases. MapReduce. Let's say you uploaded a data which is of something like 5 TB to the cluster environment. And let's say whatever the data you uploaded was scattered across something like 20 machines with all the 3 replications. Now you would like to process that because let's say whatever the data you uploaded is from something like Teradata, you pumped the data to HDFS, and on top of your 5 TB data, you'd like to perform some metric actions. You'd like to analyze how many items were sold during a specific period of time. You need to just analyze something. You'd like to analyze something. For that, you'll define a MapReduce job and you'll trigger it, specifying the file name. Now, you have 3 copies of the dataset. Definitely, framework should not process the duplicates. That means it should process any one of the copy, not the 3 copies. Point 1. And definitely, anyways, it will happen. It will not copy the duplicates. It will copy only one copy of the data. So let's say it was processing the data which is present in node 1, node 2, node 7, and node 15. I repeat, node 1, node 2, node 7, and node 15. So this is where these are all the nodes where you have your 5 TB stored as one of the copies. So whatever the chunks you have, because you have multiple 64 MB chunks, so one of the copy of all these multiple 64 MB chunks, they are getting processed on node 1, 2, 7, and 15. So node 1, after processing all your 64 MB blocks, it's gonna give you some output. Node 2 will also give you some output. Node 7 will give you some output. Node 15 also gives you some output. But on the whole, if you want to understand complete data set, definitely whatever the output you got from all these nodes should be aggregated. And that aggregation is nothing but reducer action. So reduce will aggregate the results from the mapper. Map is the place where exactly your data will be processed. So it has 2 phases, map and reduce. Of course, between these 2, there is one more phase called as shuffle and sort, which we'll talk about it much more in the next discussion, delving deeper on top of MapReduce. So simply on fly, I'd like to say MapReduce has on fly 2 phases, 2 major phases, where mapper phase, where your exact logic will be applied across the cluster, and reduce phase, where whatever the output you got from the mapper will be aggregated on the reducer node. So let me share you. So the data processing will occur in parallel because on multiple nodes, and job tracker will be the master and task trackers will be the slaves, where task trackers will be running on across the cluster along with your data nodes. So data nodes and task tracker will be running together. That's what we saw even in the first architectural level. And the jobs will be assigned by the job tracker to the task tracker based on the available slot. I think this was one of the questions which was posted earlier, I think yesterday or day before, I think yesterday, where they posted if you have 3 copies of the data sets, which copy will be processed? Which copy of the 3 data sets will be processed? Which is that lucky copy? So processing the data sets, it will always be confined to the availability of resources. Wherever it finds the resource available, that specific copy will be processed. And the resources, we address them as slots. Where slot information will be sent to the job tracker from the task trackers. So each and every task tracker will be sending the resources available from the specific node to the job tracker. So here you can see simply how exactly on fly the data processing will happen. So we know that the data will be stored across the cluster in multiple copies like this. Let's say you have block 1. So you have block 1. This is your file. Again block 1. Block 2. Block 2. Block 2. Block 3. Block 3 and block 3. Let's say you have even block 4. Block 4 and block 4 and so on. So now your data was stored across the cluster where the HDFS action was complete. Now it's time for you to process it. So obviously you'll define a jar file, submitting that jar file to the job tracker with the file name. And job tracker, since it doesn't know whether the specific file, whatever you would like to process, present in the cluster or not, so it will contact the name node, fetch the block locations on which node you have the blocks and all the things that will be returned by the name node to the job tracker. And job tracker will always get the status intimation from the task trackers. Simply I can say data node is only for storage, which will be looking after your hard disk. Task tracker are for processing, which will be looking after the RAM and processing resources. Because process definitely require RAM and processing resources, where the RAM and processing resources, because each and every node is nothing but a computer, so obviously you'll have RAM and processing resources along with the storage. And so each and every job tracker will be getting the available resources from the task trackers. Let's say the resources in this task tracker are completely busy, because it's not only your file which is being processed. There might be several hundreds of files which the clients will be keep on analyzing. So it is busy. And talking about the task tracker, how exactly it happens is like this. A task tracker will be looking after your resources, where let's say each and every machine, as I specified, you allocated 2 TB of storage, 16 GB of RAM, and a quad core processor. The moment you have quad core processor, by default, I repeat, by default, after installing Hadoop, framework will be dividing your 4 cores into equally like this, where 2 cores will be awarded for mappers, 2 cores will be awarded for reducers. And since it is 16 GB, 8 GB for mappers and 8 GB for performing reducer actions. So 2 slots for mappers, 2 slots for reducers. That's how it will make by default. So the moment you submit your jar file, definitely you don't require the reducer action, you require only the mapper action. So let's say here the mappers are busy because they were busy in performing other job, not your job. So definitely you cannot process block 1 here. So you have 3 copies, still more. So let's say there was a slot available here. So block 1 and block 4 are being processed here. And let's say there was a slot available here. So block 3 will be processed here. And let's say here it was busy. All the slots are busy. So let's say here there was a slot available. So only block 2 will be processed here. So that's how the data will be processed. And once after processing these blocks, definitely it will pop up with some output, some partial output after analyzing these blocks. And these blocks, whatever output you got, wherever you have the reducer slot available, the data will be copied to that reducer node. And there the aggregation will be performed. If the reducer slot is available here itself, whatever the data you got from these two will be copied to this node. And here the aggregation will be performed. If it is not available here, it will look after to either of these two, because anyways you got the output here itself. So you need to just move only these two. So algorithm was defined in such a way, it will always try to minimize the network transfer. So here the complete data will be aggregated, which is nothing but your final output. This is nothing but the reducer action at a high level view. Now let's delve deeper. So if you observe a peep through the slave node, where data node will be looking after your storage and task tracker will be looking after your RAM and processing resources, whereas as specified by default it will have 2 mappers and 2 reducer slots. By default it will have 2 mapper and 2 reducer slots. It's by default, they'll come up. And slots are created based on the resources available, where whatever the resources you have, those resources will be distributed across the slots. And dedicated number of mapper and reducer slots, as I specified, you will have only 2 mapper and 2 reducer slots by default. And the job will be scheduled basing on the available slot. Wherever it finds the available slot, then only on that node the job will be processed. And every task tracker, while processing, every task tracker will further create something called as task instances. So we know that, I think when you attend the very first discussion of mine, the demo discussion, on that I'll be sharing that, let's say you have a 4-node cluster. When your data was across these 4 nodes, the jar file will travel towards the 4 nodes and the data will be processed on those machines. So here if you observe, the jar file will be transferred across these nodes wherever it finds the mapper slots. The task tracker will be the jar file, whatever you have. Here the jar file will be processing, here and here. The jar file itself will be processing the data sets. So if you observe, on the whole, your data was getting parallelly processed across the cluster. Whatever the terabytes or petabytes of data you have, that will be parallelly processed across the cluster. But if you delve deeper, on each and every node, it will create further something called as task instances. And whatever the blocks you have will be further made into chunks, and those chunks will be again parallelly processed. So it's a massive parallel approach. On each and every node, it's going to have the same. Again, whatever the data you have will be made into chunks, and those chunks will be processed like this. So MapReduce is a massive parallel approach. further created into chunks and they'll be processed much more parallelly. So let's delve deeper. How these chunks will be created and why they will be created. Let's talk about them. So let's say this is how a specific slave node looks like. Let's say at this you have 360 Fermi blocks. Like this. Now, here as I specified, you'll be having the blocks, and you'll be having your slots. 4 slots. Definitely we don't require about the reducer, because once after the mappers were performed, then you talk about reducers, but without mappers you need not to worry about the reducers. Let's put them aside. And let's say this mapper slot is busy in performing some other action. So you have only this mapper slot. As I specified, if you have 16 GB of RAM, 8 GB will be allotted for this mappers and 8 GB for the reducers. In the XML file, if you configure that I'd like to have each and every instance should be of at least 1 GB, if you specify that each and every instance should be of 1 GB, at that situation, since it has 4 GB of RAM, it's going to create 4 JVM instances, provided whatever you configure in the XML file, those many instances you will be creating. So let's say if you just mention it as 1 GB, since it has 4 GB of RAM, it will have 4 JVM instances. If you specify each and every JVM instance can be of 512 MB, it's going to have 8 JVM instances. By default, we usually create it with 1 GB. So this 4 JVM instances should split these 3 blocks. So it will internally split the blocks like this. One chunk, the other chunk, other chunk. So finally, you can clearly see there are 4 splits. There are 4 splits where these splits, whatever you have, will be given as input to each and every JVM instance. And thus, it was a massive parallel approach of handling the data sets. That's how it will happen. And these colored splits, will address them as input splits. Of course, you might get a question now. What is the advantage of creating 4 JVM instances, each of 1 GB? So each JVM instance is of 1 GB. What is the advantage of creating 4 JVM instances, each of 1 GB, and then processing the data sets? Rather than this, why can't you give the entire chunk, all the 364 MB blocks, why can't you give them at once to the root JVM here? Why can't you just give that to the 4GB JVM? Because processing all these by 4GB JVM is the same, and processing here you are creating the instances with tiny heap memory. Both gonna be the same. You'll not find any better performance. But the major reason of doing the things is like this. Since you are processing the large files, it's quite usual that you may be incurred with some bad records, some null records. So let's say there was some problem in this chunk. So all these 3 blocks will be process defined, but this block, while processing, it will pop up with an exception, and this specific JVM instance will be crashing down because there was a problem with this, with a block. There is a problem with this chunk, so this JVM instance will be crashing down. So the framework was designed in such a way that for each and every failure, it's going to create 4 JVM attempts. Since this chunk was, while processing this chunk, it was failed. So the same chunk, whatever you have, the same input split, since you have 3 replications, it will be again processed on another machine. So since the problem is with data, again it will be failed. Again and again and again for 4 attempts. Even after the 4th attempt, if the processing was getting failed, the entire job will be failed because of some bad record. It will pop up with an exception. Because of bad records, the job was failed. That's how. If you just give the entire chunk, all the 364 MB blocks at once as a split to the root JVM, since JVM doesn't know on which block the problem is, for each and every attempt, it has to process all these 3 blocks. All these 3 blocks has to be processed again and again and again for every attempt, which will be a tricky task. And so the framework was designed in such a way that it will create some instances, and those instances will be processing the data like this. So that is the main reason why the input split was created. Where here you can see input split is the logical split, it is not physical, and HDFS split, the 64 MB splits, is the physical split where your data will be physically split into 64 MB chunks and scattered across the cluster. And input split is the part input which will be given as input to the mapper for the processing. You can see that here. So these input split will process your data sets much more parallelly. If you observe the very first discussion, if you observe the things here, we discussed that it's your jar file which will travel towards your data like this. So on the whole, your data was getting parallelly processed, but on each and every JVM, if you have your blocks here, 64 blocks, it will create several JVM instances. The JVM instances is nothing but the task instances, and it will create some more splits. It will create the chunks of the data. The chunks are nothing but your input splits, and will process the data much more parallelly. This is what we discussed, and that is what I just shared here in a detailed way. Right? So this is how exactly the map reduce mapper phase will be initiated. This is how the mapper phase will be initiated. And once after the mapper phase was initiated, we have much to move on, where tomorrow we'll talk about, I think tomorrow will be Saturday, so there will not be any class, and Saturdays and Sundays, only the class will be on weekdays, not on weekend. So on Monday, we'll be talking about MapReduce entire flow, shuffle and sort phase, speculative execution. There is much to talk about that. So we'll be continuing the discussion on Monday. But before that, any questions so far till this moment? Please kindly unmute yourself and you can shoot me with your questions. Please.
So,
Vignesh,
Please.
Vignesh, the last point like I didn't got that time, like my network is got disconnected. Can you repeat that one last point? Like if you have some null data in between the chunks, so how is it going to process it? Yeah.
So it's simple. So let's say there was a bad record in this specific chunk. In this chunk, there was a bad record. All these splits will be process defined. But since there was a bad record, obviously this specific JVM will be failed with an exception. And the framework was designed in such a way that for each and every failure, since you have 3 copies of the data, it's gonna create one more instance on another node and it will again resubmit this input split, only this input split to that JVM instance on the other node. So the same split will be processed again, making for another attempt. Again and again for 4 attempts. At most it can make 4 task attempts. Even after the 4th attempt, if that specific job was getting failed, if this JVM instance is getting failed, it will simply pop up with an exception specifying the entire job was failed because of some bad record present in so and so block. That's what it can do.
Okay, thank you.
Okay. Yeah. Please, any more?
yeah, Vignesh, the other thing is like we talked about map and reduce. So first the task tracker will look for slots to process the jobs.
Yeah, first task tracker will be looking for, job tracker will be looking for the mapper slots available over the task trackers to initiate the process, because always the phase starts with mappers, then ends with reducers.
Okay.
Wherever it finds the mapper slots, then it will initiate the process.
Okay. Okay.
Right? Yeah. Any more or anything still unclear, please?
Can you go to the previous screens, like where we discussed about the map, job tracker and task tracker? Previous slides which we discussed.
Right.
Somewhere we have a jar file, like we have one diagram on the 9th slide, number 9.
Yeah, this is what you can see, right? Slide number 9th slide. No?
Yeah.
Is this the one you're talking about?
Yeah, this is the one I'm talking about.
Yeah, please tell me.
So first we import we import a file, and then the job tracker.
No, we'll not import a file. We'll just design a MapReduce code. We'll define mapper class, reducer class, driver class. We'll make a jar file, and we'll submit the jar file to the job tracker. We'll mention like to process. The moment you specified it, job tracker will initially contact NameNode, verify whether the requested file, whatever you want to process, is present in the cluster or not. If present, it will fetch the block locations, and then it will look after the available slots, and then the process will be initiated.
Okay, got it.
Yeah. Any more or anything still unclear? Please. Right. So, yeah, Mr. Vishnu, hi. Please tell me. Any question?
I didn't. Hello.
Yeah. Please
Yeah,
tell me, Mr. Vishnu.
I have class today. Actually, I have college today, so I gone to school actually.
Okay.
I didn't attend the class. That's why. I want
Right,
to
no
join.
problem. So I'll just ask these people to forward you the recording, where you can
Yeah.
just talk to them accordingly,
Okay.
and you can just take the decision.
Actually, so they said that
Vishnu, sorry.
they will send us. We'll give you.
Just
Vishnu, there is another session starting from 7:30. Probably we'll be sharing you the link details. You can
Okay.
join in that session. Okay.
Definitely. Yeah. Thank you.
We'll be sharing you in a while.
Yeah.
so we shall meet on Monday again, continuing our discussion. Okay. So thank you one and all. See you on Monday.